Hello, welcome to today's Wolfram live stream. Today we have Jacopo Uggeri presenting his winter school project on hypergraph rewriting rules that produce hypergraphs with well-formed geometries and topologies. Jacopo, take it away.
Thank you. Hello, everyone. So I'm going to be presenting my winter school project. The idea here is that, so as you might know, one of the assertions of the Wolfram Physics project is to be able to replicate general relativity. And what that means is that we should be able to get an understanding of how well-defined geometries emerge from hypergraph rewriting. And so what this project was about was to try and see experimentally running some computational experiments with some I guess with some engineering behind it, so some trying to cleverly choose a set of rules that would give one such well-defined geometry. So to start, I had a look at some already well-known rules that generates geometries that do look well-defined. For example, this rule here, this cone model, this is to sort of catch everyone up. These are like Wolfram models using the set replace packlet. So they use a specific updating order that might be different based on, like, for this packlet it's defined in a certain way. It might be different for a generic Wolfram model, but we'll be using this one for this notebook. And for this cone model, starting with these specific initial conditions with just a set of self edges, we see that it immediately starts stitching a cone together, and it's always updating at the same spot, which is also interesting. From what I've seen, these kind of rules tend it's easier for this kind of rules that always update at the same end spot. They use sort of a self edge as a marker, usually something like this, or a recognizable structure, and it always updates there. These are the ones that more often produce this kind of geometries that we can well identify. Then that doesn't mean that it's impossible having multiple updating orders. I have tried, but have failed to use similar rules that would update at multiple places using multiple markers. But I think it's possible.
So
Just
just to reiterate, so this is one single updating rule, which is making a cone.
yeah,
It's not putting it at the updating events at the same spot each time, but it's like it's going around the rim, and then
yeah,
once it's
exactly,
done, it keeps going around the rim and adding to the cone that way.
exactly.
But it is just one updating rule at a time, or that's being used. So there's a lot of space to look into what would happen if you had multiple different types of rules operating on the same hypergraph at the same time.
Yeah, from the little I've seen, they tend more often to produce sort of fractal structures because they have a lot of places to grow from. So even if you start, for example, with a very simple rule that sort of adds a branch, and it can update at every branch, then it would start branching out in multiple directions, and then some branches would get very long and others less. I would hazard a guess that it would have a sort of power law distribution for the length. Um, but it could be verified, actually. That would be interesting, I guess. But yeah, it's sort of it seems to be easier when it's updating in only one place. Uh, I don't know if I have it in this notebook, but I have an example of an attempt I've tried that failed. Um, so yeah, this is another rule that is maybe even simpler than the other one, that sort of produces a sort of flat disk, and it's doing kind of the logic is the same. It's building from this edge with the self edge, and it just keeps building from that. It could go on indefinitely, and this is how it looks plotted in 3D. Another interesting model, maybe more interesting, more complicated, is this tube model. So it produces a S1 topology, which is good starting point, but it's harder to see that that is the case at the start. Although there's some subtlety here for how, in a sense, the self edges already are introducing some non-trivial topology, but then it depends how the rules use them. What ends up like the final like this one has the same initial condition, this one has the same initial condition, and they have different topologies, but in principle, if one starts with a self edge, they could, for example, expand it and make a circle out of it. So they already have some non-trivial topology. Well, at the same time, one could just keep the self edge there, like I mean, like in this case, and then the topology doesn't have a hole in a sense. So I guess it depends on how the rule develops it. Like I mean, there is still a self edge. It's just, I guess when we look at the structure of this thing, we don't care too much about the self edge. Maybe we should, I don't know, but like I think that the more interesting part is that it looks mostly flat, although the self edge is still there, and it makes it technically the structure of the hypergraph is it has some looping behavior that is not what I'm interested in when I say it's flat, but it's still there. So um the I
Jacopo, can you
yeah.
can you play some of the animations? I sent you just some now on Discord.
Oh sure. Let's see. Let me can I see. I'm gonna pause for a second. Discord. Let's see. I do have the Taurus one you sent me. Let's see. This is more. Let's see. Here. Oh, it's a tube and the.
Yeah, and
Okay. Let's see. Okay.
sent you the cone and the tube
Mhm.
on
Right.
Discord.
Here. So there's a cone. I guess yeah. Your animations
Uh-huh.
really show how the updating order is proceeding. So the cone really is. I think did you remove the you did like
Yeah,
you removed,
so I
right, you
what's
just
not being
turned.
shown here are the self edges. So there's like
Mhm.
one self edge that the rule keeps like using to pattern match with, and then it like makes a new self edge one unit to the right, and then the next one picks up there as an
Mhm.
updating event. So it kind of coils around the thing, and then this one here kind of starts from a seed and then kind of grows at one end linearly, um, making a spheroidal tube of ever longer extent.
Mhm. So this one is interesting to explore a little more. I have some examples on alterations to this rule, but I haven't explored this too much. It would be interesting to explore how to tweak this one to get maybe a torus, although that's more complicated to get it to join to itself. Um, so moving on, this was part of my project. Again, was I tried exploring initial conditions, so just running some quick experiments. I guess one interesting thing is here I used all these different initial conditions for the same cone rule, and for this initial condition with just one extra ternary self edge, it actually makes something that still looks like a cone, which is interesting, although they are not isomorphic. Even after doing some trimming, removing self edges and stuff like that. Um, But when the self edges increase a lot, then it does very different things, which is well, it's a known behavior for this sort of systems. As here I'm quoting Stevens' code 10 post, where from different initial conditions you get very different behaviors. And there was also an attempt to sort of seed initial conditions. So sort of, since the space in which one should search for nice rules, in a sense, I mean, this example here shows that it's important to also search not only the space of rules, but also in the space of initial conditions. And so the idea was, what if I only have to search in the space of rules? But this naive attempt of sort of adding an extra rule that actually seeds the initial condition, yes, it achieves that goal, but at the same time I didn't find it too useful, because yes, now I would only have to search in the space of rules, but I guess it goes in so many different directions that here I'm not really reducing the complexity of the problem in any way. I'm just moving it to an additional rule. So it didn't lead anywhere. Although it could be interesting if someone explored this more. Maybe it is possible to sort of, I mean, in principle, if the rules were not with different arities and they could interact, then there could be some interesting stuff in there in the multi-way structure, because then there is one path in the multi-way structure where exactly the same kind of updating happens as the original one. So the initial condition gets seeded and then everything else happens. But then this is assuming again that the rules could interact, so they would have like same arity, which is not the case here. But there could be different, maybe less trivial paths in the multi-way structure, so that could be interesting potentially. And this sort of idea pops up even later, similar idea of exploring the multi-way structure, so it could be worth exploring. So here is where we come to the real engineering, which is, okay, we've observed some, I guess, ways in which nice geometries can be built. Can we sort of try to artificially um, come up with a rule that does what we want? And the simplest thing, I guess, to make here, the idea was to try and make a torus. So which could be so the challenge here, I guess the initial challenge of the project was trying to make a torus. Here I just did some experiments on just using a marker. So again, this is updating. It's looking for just an edge and just keeps updating. Here it's looking for this kind of structure, similar thing. Oh, this one is one of the failed attempts I was talking about, because the attempt was to grow at all of these three self edges. So the idea was maybe it grows in a circle and it just keeps going at the same time, maybe, but that's not what it did. It might be due to the updating order of, I mean, it is due to the chosen updating order of set replace. So somewhere in the multi-way structure of this model, it does what I wanted it to do, I guess. But here it's updating, it's doing that sort of fractal updating, because it has multiple sites in which it can update. So the structure
Have
becomes
you tried the random ordering, not the
I have
default?
not tried modify the ordering, so this is just the default. Yeah.
You should try it. Maybe it's good.
Yeah,
Something
yeah.
simple.
Although is that deterministic? Like, can you give it a seed and then you
Yeah,
can
you
always
can at least fix the seed. Yeah.
okay. Because otherwise, maybe you get something cool and then you lose it. Yeah. Um. So here was the first serious attempt to start with some non-trivial initial condition that already has a hole. Um. And this is the basic idea is the same in the end. Like, if the initial condition was open, it would just make a line again of triangles of ternary edges. Well, since the initial condition already is closed, it's making a circle, and and that was the starting point, I guess. The idea will always be, and how I finally get the torus in the end, is always by starting with a closed initial condition. I guess it would be harder. I have thought about, but I haven't managed to sort of get a line to join together the two ends, and then introduce a sort of non-trivial topology via just the rule and not the initial condition. And yeah, the next attempt was to sort of build the first, I guess the most obvious way to obtain this torus was to attempt to try to get it through a triangulation. So that's why I'm using ternary edges, because they naturally will give this sort of structure with triangular faces. And so the next step is to build using using this sort of parallelograms, since I want to be able to apply the rule to something that has closed initial conditions. Then I, instead of adding to the edge, I want to split an edge into two. And this is sort of what I'm doing. I'm using this parallelogram as a single element and then splitting it into two. And this, I mean, it still makes a circle, of course. So it's basically just splitting each point. It picks a point and it's splitting it and making it longer.
But this time it's a circle of square parallelograms, or quadrilaterals, basically going stitched into the circle. Whereas before it was just a stitching of lines, edges, I guess. Okay.
And so the idea here is, let's see what this was. This is something. Oh yeah, this idea is, okay, now I want to make it 3D, so I use this element instead, which is just 3 of these parallelograms stuck together to make a sort of prism. And this is the rule that does exactly this thing, but 3 times to the 3 of them stuck together.
Wait, so this is now volumetric elements. You have tetrahedrons, 2 of them,
yeah,
and you want to make that into 3.
It's like a triangular prism, yeah. And I want to, sort of, I only have the 2 triangles and they're joined, and I want to add an extra set of triangles in the middle, so I made it longer in a sense. So that way, you can see it here, sort of, if I start with just open initial conditions, it just makes a longer tube. Unfortunately, I never managed to get it to plot this well. Maybe I should have tried with smaller ones, but you will see it better with the few next ones. Because the next attempt, well, is first to, okay, now I just put closed initial conditions. It's nice that you can start with only self edges, which is basically this starting element, but with the edges, with the triangles identified, and it's still going to do the thing, and on its own make the next element, which is like this, and then move on to make a torus. So this is already a torus, since it has sort of a minor radius and a major radius, and the topology is the one. I've played around with the meshing. There's some meshing built-in function for Wolfram models, but I haven't managed to get it to work on these. It would be nice to have an actual mesh out of these. The next idea is to simply use more sides. So instead of using a triangular prism, this is a parallelepiped, and it makes a nice tube, which is what you want and what you would expect. And then one can use it to make a torus again. And yeah, the idea is here is the same. Now here I use 7 sides, and it took a while to build this. I mean, I built this. Initially, I was building it manually, but then I guess actually I'll talk about this in a moment, because it's interesting then to try. Okay, can I grow everything from scratch instead of encoding all this information in the initial conditions and in the rules, because it's starting to get quite hefty. This again makes a tube, which is nice. and then with closed initial conditions, it makes a nice torus, which is, I guess, objective achieved, a basic objective of the project. So what I was talking about is exactly what I was mentioning is this thing about, can we avoid encoding all of this information in the initial conditions? So I have tried building this from scratch. In fact, I built this from here. Essentially, I added a rule that starting from something like this, so this element here.
That's the prisms or the tetrahedrons. This look like tetrahedrons.
Yeah, starting from the initial prism.
Oh.
Would just add another side. So instead of growing the major radius like I'm doing here, it would grow the minor radius, right? Just make the tube larger instead of making the torus larger. And that's, in fact, that's how I got this one with 7, for example. And so the idea is now one can have 2 rules, one that grows the minor radius and one that grows the major radius, and get and would have to, one could start with just this, like one could use this to grow the major radius, and and just this much simpler rule, and start with initial conditions as simple as this. The problem is that this is only updating essentially like one of these faces, and the default updating order is really messing it up. I don't have it here because this is the Wolfram community post. Let's see if I can find the it was this one, maybe the project file. What happens is that it sort of, again, it does this thing where it starts updating in different places, and so what comes out of it is not what I wanted. Let's see.
But do you have like at least multiple rules that you can try iterating those? Like maybe make an iteration using just one rule, then using another rule, so that you can control it.
Yeah, that's another idea. I guess I was really hoping I could get it to happen naturally in a way without forcing different phases. Like, okay, you do this, then I stop it. That's sort of what I did, right? I used to get this initial condition. I actually used a different evolution and I stopped it. This one, is it this one? Yeah, it's this one here. So it doesn't look that nice here with the rule, but it's sort of grow. Oh, is this? No, this was an attempt, but it did something wrong. But this one is growing it. So it's starting with the cube, and then
So
it's
can you just activate this one again and make your torus fatter? You know, in the
Yeah.
smaller radii.
Yeah. This is, it could be done. The mistake I did was just mash the 2 rules together, but then since the updating order does not know what I wanted to do, it's picking different sites, not in a sort of, I guess, a coordinated way, and so it's growing it in different places more than others to keep the structure I wanted, and so it's not doing what I want. And here's another example. What did I change? Here I'm really starting, okay, I'm just growing this should be growing the major radius, and this should make it fatter, right? But then since they get applied with different order, the orders don't follow, like they don't know what I wanted to do, and they have more freedom than what I need, and so they do stuff like this, which is cool, but it's not what it needs to do. And but yeah, then I guess the next step is sort of what you were saying. It's try, okay, no, yeah, here I sort of resigned to just build it from here. is trying to grow it in this way with both rules. And I guess here it also comes back what I was talking about the multi-way structure, because technically what I want to happen is already in the multi-way structure of this, right? If I choose the right updating orders, then it will build like, okay, it can make it fatter, and then it can make it longer, and then maybe, you know, if you choose how to move in the updating in the multi-way structure, you can say, okay, now make it fatter a little bit more everywhere, and now make it longer. Or you could even have it like fatter in some areas and larger in others, I guess, if you wanted. But on its own, it doesn't have enough restrictions to do that, so it does all of this. So that is one, I guess that is one avenue for extension for this project. And I think here was an attempt to get the meshing. Yeah, it always blocks my computer. And yeah, this was another attempt. But yeah, so this is one avenue for exploration. The other is instead modifying known rules, which is what I was talking about at the start about the balloon. The S1 is, okay, can you modify this rule to get the non-trivial topology that you want? Like, is there some clever tweak maybe to the initial conditions, or adding some extra rule that, since, you know, there's already a good starting point, maybe we can use that to make a torus or something more interesting. And so this is a very basic attempt. Okay, can I just join it and have two of them grow together? And I mean, of course, like the updating and the rule, the system itself doesn't know that there's two of them. It just knows to go pick the spot it's looking for and update it. So now it's growing two of them. And then you can also join them. So here it's the rule is basically two of these rules joined by a self edge, joined by a binary edge, and it's also duplicating that binary edge somewhere else. And so it's basically just growing the two balloons in parallel, and then the embedding puts them one inside the other.
And they're connected, right?
Yeah, they're connected. So it's one inside the other, and that it's basically sort of a mirror. It's like
they're connected at the poles. It looks like
they're connected everywhere. Like each of these.
Oh, I see.
Can I zoom in? Each of these is connected by a binary edge. So it's essentially sort of a slightly. It has a thickness in another dimension, if you want. You could think of it that way, right? And yeah, this leads to the same, very similar result. I just swapped the edge I was duplicating, and it's a very similar result, although it's not the same, at least even different ways. I've tried trimming it in different ways, but it doesn't say it's isomorphic. So I haven't checked thoroughly, but it looked like they're not. I mean, I guess no, yeah, it doesn't. It looks like they are, but they're not. Yeah. And yeah, this was the end of sort of the project. I guess I can talk about some other things I've explored during the winter school. Like, this was a small aside I added as an appendix. Unless, but I can maybe I should ask if there's any questions now before moving to this. Okay. So
Well, I have a comment, but I'll save it for after this a little bit.
No, it's fine. Like,
yeah. So I mean, talking about different rules, you know, one thing I was thinking about was, okay, you start off with something that gives like the topology of a sphere, like that tube or something like this, even, and as one rule that grows the spheroid. And then you could implement like another rule which goes into that and like pinches it somewhere and makes a hole there so that it changes the topology in one updating event, and then you could go back to some other rule which like propagates and expands that new topology. So you have like growing and then like a discrete change.
Yeah, like I think, I mean, there's a lot of freedom, right, to do this sort of thing, I guess. I think the question is, I guess, how you want to do it, because like if you want to just give the system the rules and let it do its thing, then the only way I could think of sort of encoding, okay, now at this moment do this, is to sort of give it a rule that takes the whole state at some point that you know it's going to reach with the other rule, and then does the thing you want. So it's I guess a very naive implementation of just, okay, let's say we evolve this to here, and then we take this state and we say, okay, take this state and add a hole in it. So we make a new rule here that says take this state and add a hole in it. So when it reaches there, actually, I don't know, with set replace, it might just go on with this. But yeah, that's just the implementation problem. Maybe if you put that one first, it's gonna try that one before this one. But that's just a technical detail, I guess. And then it would add that, and then I mean, hopefully it would stop. Although maybe if the rule sort of in the future gets back to a similar configuration in a subgraph, maybe it would also apply that. That could be problematic, or it could be what you want, I guess. But that's the way I thought you could do something like that. I guess you could also do that for joining the two ends. For example, for this torus, you could start with this and let it grow, and then at some point say, okay, when it grows that large, then join it. But it feels like you would be encoding much more information in the rules. Like you would be essentially just very explicitly forcing what you want to happen already in the rules, which I guess is fair, but it would also be more satisfying to get it to happen from less information, right?
So yeah, I mean, if you had like this spheroid and then you want to say, I want this end to be glued to this end, then you would need a updating rule which captured this corner and this corner, this piece and this piece, and they're disconnected pieces, and then you connect them.
Yeah, I think
I'm
the
not
problem,
sure
if you just add any rule that does that, it will start connecting everything, right?
right, unless
Because
there was some identifier marker on, like, oh, you
yeah,
have a collection of self loops that has a particular structure on the endpoints that you want to glue up.
yeah, you have to do something like a little bit more clever, I guess.
But is it possible? Because like most of the rules that we look at are sort of this connected piece morphs into this other connected piece, and it's never like, oh, I want to take one piece and split it into two disconnected things, or take two disconnected things and make them into a different piece that is connected. Have you looked at that, or Nick? Have you seen anything like that? Does that
Not
make
too
sense?
much. Yeah, I've had some ideas, but I mean, I started by sticking to the most basic things, although it would be interesting to explore that too. I mean, potentially you could also do it from here, right? You could take this and say, okay, can I join these two? Maybe you have a rule that replaces this, maybe over multiple updates, replaces this binary edge with another structure that grows in and is gluing these two. So so then you can have a rule that attaches this binary edge in one place, and then you go from there. I don't know. I think the problem with these things is that you're sort of fighting against the rules because they try to do whatever they can, and most of the times, especially at the start, it's not what you want it to do. But I guess if one approaches cleverly, I think the biggest problem is that if you don't constrain it enough, it's gonna start doing what you want at some other place, right? Yeah, but if you if you constrain it too much, you're basically giving it all the information already. So I mean, as I said, it could be interesting, but at the same time, it's kind of obvious because if you already forced it to do exactly that, right? Yeah, so I guess I'll move on to this small bit, which is about, I guess it's sort of the same ideas come back. This was trying to say, okay, well, can I replace ternary edges with binary edges? So can I map it to binary hypergraph, to just a graph, and then do the same evolution? And the problem here is that the mapping is it's not bijective, in the sense that what these here, I mean, I can preserve the orientation by using binary oriented edges, but it does not preserve, I mean, to be fair, it also doesn't preserve, although that could be fixed, it also doesn't preserve the start of the ternary edge. Like this edge here is explicitly going from here, but this edge here is going all the way. So there's some ambiguity there, but that could be fixed by using, I think, just 2 binary edges instead of 3. Although those then wouldn't have the triangular structure. So, well, maybe one could use one less. These have 2 edges going in all directions. One could use one less, and maybe that would fix it. But there's also the problem of the ternary edges. Here is just the information of which edges were ternary edges gets lost. So here I could pick any loop of binary edges, which could include maybe this one and this one, and it would and then sort of take different pieces of things that were originally different ternary edges. So then the mapping would not be bijective in a sense, which is what you would expect, right? The ternary or higher arity edges are encoding more restrictions that you don't have to put in by hand, but it's already in your updating structure because you are using higher arity relations. And what we observe here is, of course, that the evolution is different. This is the cone rule, sort of mapped to binary and then evolved, and it naturally stops here at 26. Again, this is with this updating order, while the normal cone rule just goes on and on and on. And I guess the interesting thing again here is about the multi-way structure, because then if I look at the updating order, I could enforce that this updating only applies where there would be a ternary edge, and that would just be picking a path in the multi-way structure of the binary one. So in a way, I guess you could say that the multi-way structure of binary models is larger, and it includes a lot of ternary and I suppose also higher arity models. Although maybe to get specific arities you would need the specific rules, yeah. And yeah, so that's the end of this. If there's any questions also on this part or on the whole thing, there's a lot of hints of things that could be done. Like there's more that could be done in many different areas, I think, even just from this.
Did you so you working with edges that are connected? You worked with triangle elements, triangular prisms, tetrahedrons. Did you ever work with like cubes?
I mean, the tetrahedron you're referring to.
Maybe it's a triangular prism in disguise here. Looks like.
Yeah, it is. like here it's just the embedding is deciding to show it this way, but even with the cubes, it does that thing. Like I mean, it's not, again, it's more than a cube. It's like it's like a
Oh, that's a
rectangle,
parallelepiped. Yeah,
yeah,
so that's like a
parallelepiped. Yeah, this
three-dimensional cuboidal. This is a skewed
so this is
cube.
a starting element, and this
Mhm.
is a sort of duplicated one.
Mm-hmm.
Or if I split it in the middle, it's the same. And yeah, it's sort of the same idea. Here it's done with seven-sided prisms. Although, do I? I never plot it in 3D. Let's see, but it is this one. Could plot it in 3D. Let's see. This is the. So it was graph. Oh, I'm already plotting it here, right? Yeah, it doesn't plot it that nicely. I guess I should. I could do. Still, yeah, it doesn't look that nice. I also think it's hard to see with some embeddings if I messed up the the orientation of one of these. Maybe it has sort of a kink here, or if it's just the embedding that's tricking me into thinking that it sort of looks a bit asymmetrical. But this is the same idea, right? Then you could have.
Yeah, I wonder if the self loops are like throwing off the way that the embedding is being
Oh
calculated.
yeah, maybe yeah. Then yeah, I was talking about it. Don't have it here.
I have a
It's
question.
yeah.
I just, or maybe two, but just firstly about what you were saying towards the end. I think there are ways to think about like evolving the arity of the hyperedges in one direction or another, like based on maybe, I mean, there's multiple ways you could do it, but like you could think of the kind of set theoretic relationships, like, okay, well, maybe if these two hyperedges intersect at like a point, a vertice or more, and like you could think of even symmetries, like if they're connected by like hypergraph automorphism, then you would kind of like you could say then you evolve those two and on that vertex set to a higher arity hyperedge if they're say like connected by symmetry and maybe they intersect. There's a bunch of ways to do it, but like those are kind of well defined in the sense that they like use the hypergraph properties that are there to sort of, you could think of smoothing or like making it more discrete. You could go in either direction, but and then, just a more general question. What do you mean by like when you say the hypergraph has like a torus topology? Like, is there a formal kind of notion for that? What you mean by that?
That was actually, that's a good question. That was actually one of the first things I worried about, and then sort of we decided to focus on getting something that looked like a torus first, because it's a good question because exactly sort of like on this, I guess, sub level, like on the level of the just structure of the hypergraph, for example, any self edge will already mess up the topology, right? It will not be a clean torus anymore. So in a sense, this torus topology is intended in a sort of coarse grained kind of way of, okay, I take the hypergraph I get, I turn it maybe even into a graph or in a triangulation, and I get a mesh out of it. That look like a torus. If it does, then I guess that's a satisfactory answer. But it is interesting if that, like, I guess this is it's sort of an intuitive choice and maybe an easy choice. It's interesting to know if that's necessary. Maybe, from the point of view of the Wolfram model, the model doesn't know, that looks like a torus to me. It only knows its own topology, including the self edges and everything.
Mhm.
So sort of
Yeah, no, that's interesting. And then okay, so that's kind of what I was thinking. Like it's more just like if you can imagine it being like uh, a surface instead of discretized like that, then and it would then roughly basically resemble a torus, like if
yeah.
it's just a strip instead of these like single edges. And then I don't know if you've tried this, but I haven't done much with rewriting, but maybe there's something to like generating with rewriting this kind of generic but detailed hypergraph of some kind that has the capacity to contain a lot of interesting substructures, maybe some of these things as substructures, and then you stop it at some point when it's sufficiently large, and then you can do some reverse like deletion type stuff based on whatever internal properties you're looking for to kind of, I don't know how that would be implemented exactly, but I just thought there might be a difference as to directly constructing it versus like maybe you're actually whittling down from a larger space that has the capacity to contain a lot of like maybe interesting substructures might work, but deletion maybe goes differently. I'm not totally sure.
Yeah, substructures or support structures. Like, in 3D printing, you print this thing and you have to have like these things that tilt it up. And then you knock that off as a refinement process afterwards. So there are things like crucial to the construction of the thing that you want that are auxiliary to it. And then there's a refining process. That's
I think that's an interesting way to like an interesting direction to explore in the sense of you could use rules that do this sort of deletion for you, right? And I guess it's the same question of you have to restrain the rules enough that they don't mess up at the start, but only at a later phase. Although I guess at this point, since this thing comes up a lot, maybe it would make sense to say, okay, what if I decide that I can give different phases to my model? So use this rule for this number of events and then use this different rule for this number of events. And yes, I'm artificially deciding that, but I guess in a sense it's about moving in the rule yad at some point and moving to a different rule and seeing what happens from there. And I guess it's curious because you can essentially just define different phases of your evolution, which could be interesting not only for the physics side of things but also what Stephen was exploring recently about biology. Like, for example, things like the fetal development or stuff happens in different phases. So I guess you could emulate something like that with this kind of approach. Although it would be interesting if you could do that sort of naturally. Maybe I'm just hoping too much, but if you could get rules that do what you want when you want it without you imposing extra restrictions on them. I guess it's not possible in all cases, but maybe there are some cases where that is possible, and that would be interesting to know, I guess. And
oh, sorry, just one like last detail that might help with the implementation is like if you're thinking about graph, I mean, you could even just think about like starting with graphs as opposed to hypergraphs and doing graph rewriting. But like if you use particular, like, I don't know, you generate some generic, like this generic space that could have a lot of detail within it. Like you could preserve nodes, like say a triplet of nodes that satisfies some like, I mean, if say the graph were representative of some like algebraic structure or like ordered structure, then maybe you could use those kind of identities to say like, okay, well, when this triplet of nodes like satisfies modularity of some kind for like, and then you would get the kind of resultant graph that you're looking for. Maybe you delete the ones that don't, or I'm not like super familiar with the rewriting aspect, but that was just one other thought I had.
I mean, it's interesting, like in terms of like, I think what you're saying would require in most cases a modification of sort of the basic algorithm because what it's doing right now is it just looks for this combination of edges. I think the self edges, no, sorry, the non-self edges could also be self edges. Like in fact, as you see in some initial conditions are only self edges. But so I think for stuff like you were talking about deletion or deleting stuff that doesn't satisfy certain conditions, if you could potentially include some of that in the rule. But at the same time, it's also sort of what you were saying sort of suggested me this idea of maybe you could have a negative rule that says, okay, don't do anything to these set of nodes. So that's sort of like a negative rule, right? Instead of saying that fix these ones and don't touch them, because the way it's done right now, I don't think that would be possible with just rules. You would need to modify it, yeah. But it is interesting. Should that be included in these systems, maybe? And yeah, I guess I can add another thing about what I was thinking related to the systems, and this is sort of a question I have. So if anybody has an idea on this, is that here, for example, I used ternary rules, and because I just wanted a triangulation, and I have seen other structures that already use them and get triangulations. So the question is, if I wanted to get geometries that are not surfaces or things that live in 3 dimensions, but instead is something that is, for example, 4-dimensional. I mean, I guess in a sense, this one is 4-dimensional. In a sense, it has some thickness in a 4th dimension. But like if I wanted to get something that is like a simplicial complex in 4 dimensions, so like uses tetrahedral faces instead of triangular faces, what sort of edges would I use that naturally give me that? Because for triangular faces, I would use ternary edges. For tetrahedral, you would think maybe quaternary edges, but then I should prove this or look for a better confirmation, but I feel like a quaternary edge has less information than sort of a tetrahedral edge, right? A quaternary edge just has 4 points in a certain order. It's just a relationship between 4 points in a certain order.
Right,
But
like the difference between a quadrilateral face and a tetrahedral volume element.
Yeah, it's missing some orientation information, no? So interesting.
Well, so like a quadrilateral, you can kind of make a circuit around the border and call that the edge that you're looking at. For a tetrahedron, you could say like it's a complete graph on 4 vertices. You have 4 triangles in there, let's say. I don't know, but that's like a simplicial complex that you're saying. Like you have a set with 4 elements, and then you have every triangle within that, and then every edge within that.
Yeah, so my question is sort of like, is there a relationship? Like I'm not sure. Maybe I'm wrong. Maybe you can get that with just sort of normal higher arity relationships, which I would think a quaternary one, but maybe you need more, because I feel like quaternary one is missing some information. But like, is there such a relationship to encode just naturally this sort of like the whole tetrahedral edge, in a sense, like how there's a ternary edge would encode a triangle, although with some orientation, which is something, again, the tetrahedral one would include the orientation of the faces and of the volume itself, which I don't think a quaternary edge would do, but maybe I'm wrong. So it's sort of an open question if anybody knows.
Yeah, it'd be
Or has
interesting to
think,
look at like polytopes, 4-dimensional polytopes, like pentacorons, or the
Sorry?
triangle, tetrahedron, and then a pentacoron is the next. It's a 4-dimensional volume element, simplex. It's just the next one up. But then, like, so you can, I guess, in 4 dimensions, what you do is you take tetrahedrons and you stitch them together to form like a 3-dimensional volume that wraps up in strange ways in 4 dimensions, like a 600 cell, for instance.
And my question is
four-dimensional and analog.
it's not about that. It's about, can you make an edge, a sort of a relationship that you can use in hypergraph rewriting that naturally produces objects that have sort of tetrahedral faces, so that would naturally be 3D slices of a 4D space, I guess, if you embed it. Right? As the same way you get a surface that is triangulated if you use ternary edges.
I mean, I think it depends on how literally you want. Like, this is why I think the question about what the hypergraph is it what it is, or is it kind of reflecting it, or just because you could actually think of the actual hypergraph as an abstract simplicial complex, where you say, for this example, like you have the subsets of 4 vertices that are the 4 faces, and you would have that downward closure in the sense. So you would have all those ternary, the 3 hyper edges, and then the regular edges surrounding that. Like, so, but I don't think that's exactly what you mean. So I think because it's not exactly like what, because the hypergraph could literally be that, depending on how it is. It would be, by definition, be an abstract simplicial complex. But like, do you mean that it kind of emulates that? Like, I guess I think you would have to clarify like what the interpretation is.
It's a sort of intuitive definition of like, okay, you look at this, and it's except for this last self edge, it's the triangulation of a cone. And so the question is, and it happens because I'm using ternary edges, and so all of these are ternary edges, right? So the question is, can I get those ternary edges by the sort of, can I, is there such a relationship instead of ternary, such that I could do something similar and get something that has a 3D surface that is made up of tetrahedra in the same way? So it's simplicial complex that is sort of enclosing I guess a volume, like in this case. But I don't think that's necessary. What I really want is like, is just thinking, okay, is that, I'm curious because it's like, is that just, a normal hierarchy relationship, or is it a different kind of relationship? Is it like a more complex kind of relationship that would encode this sort of information in the same way? I don't know, maybe it's an ill-defined question. It feels pretty intuitive to me what I want it to mean, but maybe it's not.
I'm not sure I parsed your question very well. Can you rephrase it or repeat it?
Right. So here I have I'm using ternary edges.
So basically triangles. Yeah.
Yeah, and I get triangles, right?
Right. Yeah. This triangular mesh, and the rule is operating on triangles. Yeah.
Is there a tetrahedron you can use to get tetrahedrons that enclose some? That give you like some and I mean, doesn't have to be tetrahedron. It could be in general. Give you some n-1 dimensional surface in n dimensions. Like this is a 2-dimensional surface in 3 dimensions if I embed it in 3 dimensions.
Yeah. So like the hypergraph is operating on the connections, and so it's purely a topological process. And the reason why it comes out as a cone is when you take that topology and you try to embed it in 3-dimensional Euclidean space using spring electrical embedding, for instance, then it fleshes out to be this shape. You can also embed it in 2 dimensions and you get sort of overlapping necessarily, or you can embed it in arbitrarily many dimensions and get some computation result that might be a little bit more wild, or
but you can see the surface like intrinsically, right?
Yeah.
By some metric, like measuring balls on the hypergraph and stuff like that, right? So for example, if you had, so my question is not about what you get, it's more about is there such a relationship that is to tetrahedra what ternary relationships are to triangles? Put in very simple terms. But yeah, it's like, and is such a relationship just a simple hierarchy relationship? Is it just a quaternary relationship, or is there some extra information that you need? Because I feel like you need more, but maybe I'm wrong. But yeah,
Definitely some things to explore on that direction.
Okay. And if just saying, if anybody has any extra questions in the future or watches this recording, you can ask me questions in the Discord too, the Wolfram community, Wolfram Institute.
Awesome. Thank you, Jacopo, and just want to make a reminder, announcement. Tomorrow we're having a community forum on Discord at 2 p.m. Eastern. So keep an eye out for that. That's going to be on the topic of philosophy. Yeah, so that's going to be an interesting discussion then. Thank you once again, Jacopo, for presenting.
Yeah.
And thank you all for tuning in on the live stream.